next slide. Okay. Great. Okay. So first of all, I'd like to thank the organizers for inviting me to this beautiful place and the opportunity to talk my work. So this is a work I have been doing with Michael, where he already mentioned in his talk. I will talk about the modular forms in type 2B string theory and U1 violating amplitudes. So basically, we are interested in string collections to Einstein help the action. So in the form of like high dimensional operators. And as Michael said in his talk, those coefficients of those high dimensional operators, they are very interesting functions, depend on the moduli. And so we basically ask, based on symmetry, how much you can say about those functions. So here at least some of them which are well known, and it was already mentioned in Michael's talk. But there's a ... and so we're trying to extend our understanding for those ... So here's the plan. So I will briefly review those known results. Actually, you already see in Michael's talk. Then we will try to derive those known results from amplitude point of view. Actually, it's generalizing seeing and his collaborators method. And so extending the derivation allows us to talk much more general interactions. We will see. So I think you already see this kind of notation in Michael's talk. So we will discuss interaction take this form. So let me just remind you again. So this notation just means you have M fields, and this W indicate the U1 weight of this interaction, and there's a P indicating how many derivatives do we have, and I so denote the possible degeneracy of the how you construct the derivatives, and we are very much interested in the coefficient of this interaction, and we will try to say something how supersymmetry when you implement the in terms of amplitude constrain these coefficients. In particular, we will try to derive some differential equations for those coefficients. So, okay, let me review. Well, so obviously I'm repeating what has been discussed in Michael's talk. So we have this non-holomorphic modular forms. They are functions of this moduli tau. They transform in this particular, so I will go quick because it was discussed before. So it transforms in this particular way under SL2Z symmetry. One important point is that when you take this modular form, when you act on a covalent derivative, it changes the weight. So in particular, there are two kinds of covalent derivative. One increases the weight, the other one decreases the weight. And I emphasize, so this is like, I will often call this as like a simple derivative, then covalent derivative is shielded by a constant related to the weight of these functions. So for the purpose of this talk, we will only focus on the case where W pi is like minus W. So here some well-known example, namely the Einstein series, or non-harmonical Einstein series. So I guess you already saw this in Michael's talk. Yeah, they defined like this, and they satisfy again, probably you saw before, they satisfy this Laplace equations. So here are the well-known example, nearly r to the 4, d4 r to the 4, and d6 r to the 4. So the coefficient of r to the 4 simply the Einstein series. So the coefficient of r to the 4 and the d4 r to the 4, they are Einstein series. They satisfy this homogeneous Laplace equation. So they have perturbation expansion, which can be checked explicitly by string computation. And for the d6 r to the 4, it satisfies interesting inhomogeneous Laplace equation. The first, this equation first appeared in a paper by Green and Van Hall, and later Seeing and Yifan Wang, they rederive or understood this equation from an amplitude point of view. And this is the method I will review, and we will generalize it for more general interactions. So they derive this equation as a Laplace equation, namely, two derivative equations. It turns out somehow it's more convenient, but not so different, but it's more convenient to derive first order differential equations. Okay, so I will talk about the amplitude. So in the sense that so when we talk about the amplitude, we mean that we have a fixed background. So we are talking about say flat space, Minkowski 10-dimensional Minkowski space. The metric is eta mu mu. On there's another background, so tau. We also fix background for this moduli. Then we look at the fluctuations. So I call delta tau. So this coefficient appears, say, r to the 4 or d4 r to the 4 is a function of moduli. So you should expand it when I talk about the scattering amplitude. So the expansion is like, it's like this. I just defined my fluctuation normalized in this particular way. So for example, take r to the 4. Say the coefficient is f0, so I expand it, so you can get the higher point interactions like a 5 point, a 6 point. So this is an example. Say my weak line always a fluctuation, so this is the way you get the say 6 point interaction. Okay. There are a few things I should comment here. As you see from here, when I do the expansion, as you see, I got the simple derivative instead of covariant derivative I emphasized before. This is, of course, related to the fact that the fluctuation tau, delta tau I choose does not transform properly under the U1 symmetry. Another way to see the problem is that if we just look at the two derivative action, say like this one, you expand around the background, and you see that even the two derivative action, namely the classical supergravity, has U1 violating terms. Of course, we know that in supergravity there is no U1 violating amplitudes, and indeed all those U1 violating interaction actually vanishes onshore. Okay, so obviously what one should do is that, well, okay, I will comment on that. So on the other hand, however, when you have, although those two derivatives U1 violating vertex does not contribute to supergravity amplitude, but they do contribute to string amplitude. So when, for instance, in string theory, there's, for instance, there's a high derivative interaction like R to the 4 tau hat. Then you can attach this U1 violating a 2 derivative vertex to this one to generate the, say, 6-point amplitude. And this contribution combined with like something like this, precisely make it a covariant derivative, okay? Of course, this is complicated to do it, so you have to do it like the Feynman diagram by diagram, but there's a systematic way to do it, namely to do a field definition to get rid of all those onshore vanish interactions. And it turns out that the field definition takes this simple form. Well, anyway, you can figure out what is the field definition you should do, such that to remove all those onshore vanishing vertex in classical theory. This, of course, is very, very standard. That when you expand a sigma model, you should expand in this normal coordinate, and this is the normal coordinate for this SO2R model U1 coset. I should probably my colleague mentioned this is the field John used in his formulation for the classical type 2B theory. So this field, we define the field B, does two jobs. One, be transformed nicely under the symmetry, so it transforms linearly. Second, as I mentioned, it removes all the U1 violating vertex. Now you can see that say you expand a function or moduli. So it was a simple derivative before, but now if you rewrite it in terms of B, it all became covariant derivative. Okay. Then there are other fields, so one should do the same thing for all other fields in the theory. For instance, there's a two derivative term in the classical theory. Again, if you expand around the delta tau, you will see that this guy will generate an infinity number of U1 violating terms, which all vanish onshore. And now you do field definition like this one. This will kill all the U1 violating, but onshore vanish vertex. The second, only after this field definition, this lambda pi transform nicely under the symmetry. Okay. So in summary, I just point out, so all the interaction, when you choose appropriate the fluctuation fields, all the interaction indeed manifestly SL2Z invariant. Namely, if you expand all those coefficients are covalent derivatives on the modular functions. So with this kind of introduction, we are ready to study amplitudes. So here I will use a 10-dimensional spinor helicity. So in 10 dimension, maybe you are, I don't know, anyway, in 10 dimensions, so a momenta, a massless momenta can be written as like a product of two spinors. Here, the capital index A or capital B are the spinor index of Lorentz group, and the small index little a is the SO8 little group index. Okay. So this lambda, if you just count the number, lambda should be constrained. However, it's not important here. then you can introduce supercharge. So to describe supersymmetry, we also introduce fermionic variables. Grassmann variables we call eta. Eta has so 8,000. Eta carries again the little group index. So there's 32 supercharges. So 16 of them take this form. So A long from 1 to 16, and the conjugate guy takes this form, and you take the anti-commute between these two, and you see go back to the momenta. Okay. Using this Grassmann variable, you can package all the onshore degrees of freedom into a superfield. So basically, they are polynomials.
This seems a kind of a covariantized like cone in a certain sense, because remember the degrees of freedom you have, the lambdas are essentially the degrees of freedom you have on the like cone.
Sorry, lambdas.
Lambdas.
Yeah.
And the way you write, okay, everything works as if you were just almost using a light cone.
Yeah, kind of like cone, but
this is why you say covariantized, because it's covariant, but you have the degrees of freedom of the light cone.
yeah. So this only has short degrees of freedom, and for each particle carries its own little group index. So it's a massless. It's a massless momenta. So there's a transverse direction. So yeah, so we have this superfield. You probably saw before. Yeah, so we have this superfield. It's simply a polynomial of etas. So you expand the polynomial of etas, and then one can assign the U1 charge to the field. In particular, we have, say, in our convention, we have this B field, which has a charge -2, and the B bar has a charge 2. In the middle, there's a graviton and the self-dual file form, which has a charge 0. Okay, I see.
Those etas are the same as the slides before. You use lambda and etas.
That's right.
Lambda are bosonic.
Yeah.
Eta are fermionic.
They are Grassmann variable.
Okay.
Yes. So the super amplitude should be inherently, it should be killed by supercharges, because I want a supersymmetry. So one way to make it manifestly killed by a half of the supersymmetry is that I just put the delta 16 here. So if I activate this amplitude with Q, because of this term, it's manifestly killed. And then I will require what's the remaining part is killed by the remaining 16 supercharge. So this will be my requirement on this function. So just a comment that in supergravity, there's only U1 conserved amplitude just by counting it. So this function must go like eta to this power such that it preserves the U1. However, in string theory, one can perfectly have a U1 violating amplitude. In particular, there's the simplest one is called the maximal U1 violating amplitude. Namely, it violating U1 maximally. In that case, the remaining part has no dependence on eta. So the remaining part will be only function of Mandelstam variables. And here I have been written in a form in the sense of alpha pi expansions. So, namely, if I compute this maximal U1 violating amplitude, then I do alpha pi expansion, and the P is indicated which order in the alpha pi expansion. Okay. So the remaining part of this super amplitude, it turns out to be simply a polynomial in Mandelstam variables. Namely, they don't have poles. That's simply because this amplitude, I mean, so suppose that the pole, it will factorize into two lower point amplitudes, but that's the minimum number I should have, so there's no way to factorize it. So therefore, this is a polynomial, and it's actually a symmetrical polynomial, because I'm talking about a super amplitude, all the states are the same, so it must be symmetric. Yeah. So here, the coefficient is a function which depends on the coupling or the moduli. Okay. So again, this I is denoting a possible degeneracy. So I think Michael mentioned if you are more familiar with 4 dimensions, so in 4 dimensions, this maximal U1 violating amplitude is a KLT of MHV and the anti-MHV. So you may know that there's a so-called orthogonality of KLT, namely in supergravity, the only non-vanished double copy is the copy of 2 amplitudes which has the same helicity. So here, this maximal U1 violating, I take opposite helicity also. So that's why they're actually the simplest amplitude to consider. As often, this theory has this coset structure. As often when you have coset structure, the amplitude satisfy so-called solved theorem. So in the case of supergravity, so you may know that in the solved limit, just like so-called pion or at the 0, the amplitude goes to 0 in the solved limit when you take a pion to be solved. In this case, because the symmetry is broken and the limit of the solved dilaton actually is non-vanish, but we know the result of the solved limit. In particular, so I already separated my amplitude into a kinematic part and the coupling dependent part. It turns out that the solved theorem tells us that when you take say n point, you take one complexified dilaton to be solved. It turns out that it relates the coupling part by the covariant derivative. So this is like higher point related to the one lower point by a covariant derivative. So here n-4 or n-5 denoting the U1 weight. And the kinematic part just go from higher point to lower point. Okay. So some of you may be more familiar with the solved dilaton theorem by Paulo and the cooperators, where you have the alpha pi d alpha pi, so I'm translated to Einstein frame now. And if you remember, the covariant derivative is tau 2 d tau plus w. So this w is coming from when you take the action to be solved. So when you combine these two together, make a covariant derivative. Okay, let's look at some examples. The simple case is the one related to r to the 4, but I'm talking about the higher point of the same number derivative, so namely dimension 8. In this case, this polynomial is just 1, so there's a unique one, of course, just 1. And the coupling is related by the covariant derivative. So in the case of r to the 4, the coefficient is the Einstein theory, and when you go to higher point, they are just related by activated by covariant derivatives. And then the next one is d4 r to the 4. Again, there's a unique kinematic structure. It's just Sij squared and the sum over permutations. So in the case of d4 r to the 4, the coefficient is Einstein theory with s equal to 5 over 2, and the higher points are related by covariant derivatives. Okay. So things become more interesting at the order of d6 r to the 4, namely dimension 14 interactions. So this is a known fact. When you go to s to the q and n bigger or equal than 6, there are two kinematics imbalance. It's obvious because one of them should be this one. The other one is this one. So one is like Sij to the Q, the other one Sijk to the Q. Sijk became independent from Sij only if it's more than 6 points. Right? And it turns out that there's only two of them. Of course, you can choose randomly two independent ones. However, we will argue that there's actually a unique canonical choice of which two should be independent, and given by here. So the first one is chosen such that it agrees with what you will compute at the tree level. So, namely, you do a 6-point string amplitude computation and expand it to this order. You see this guy appears. So, actually, this was computed by Oliver Schroeter in his unpublished work. Then, according to the solved theorem I mentioned, this guy goes to 5 points, which is unique. It's 5 points is like Sij to the Q, you sum over permutations. And the coefficient are related to the 5.1 by a covariant derivative. Then the question is, what are you going to choose for the second one? Of course, anything I choose different from the first one will be independent from the first one. However, I would like to choose the second one such that does not affect the solved theorem I mentioned, right? Because I want the solved still satisfied. Therefore, I want to choose my second one such that it goes to 0 in the solved limit. And it turns out that there's a unique one. In fact, it's obvious at the 6 point, that's the only thing you can do, right, at this order. So when you make up something like this, it's like P1.P2, P3.P4, P5.P6. Therefore, by construction, and this is the only construction, only one you can have, such that this object will go to 0 in the solved limit. So one comment is that this object, as I said, is construct vanish in the solved, has a nice property. Namely, if I will write a Lagrangian for this interaction, it will be Lagrangian with no naked tau. By that I mean this tau field always appears with derivative activity. That's very important because if you have naked tau, it won't transform properly under SL2. Right? Okay, so as I mentioned, the first one is related to 5 point by a solved limit. Therefore, the coefficient of this guy is related to the 5 point by a covariant derivative, and the 5 point again related to the 4 point, namely d6 out of 4 by another covariant derivative. And we know very well about this coefficient. In some sense, this one is not so interesting because we know everything about it. What is interesting about is the other guy, which is new. So we will try to constrain the coefficient of this operator. Before do that, let me just review how I would derive some constraint for the first one. And this here we generalize, well, I remind you a method by Xiying and Yifan. The idea is the following. So if we want to study the coefficient of this d6 out to the 4, say the coefficient of, I call it E0 here, what you do is the following. Maybe it's not so clear what I'm reading here, but you will see very clearly next slide. So basically what you do is you look at the 6-point amplitude. 6-point amplitude with, for instance, with 4 gravitons, so H is a graviton, and the 2 B fields, actually it's B and the B bar. Okay. Then I won't be able to say the detail here. If you are interested, we can discuss later. Then it turns out that the corresponding super amplitude, it turns out that just because of number of derivative and the number of eta, the corresponding super amplitude cannot have a contact term. So if it cannot have a contact term, it means this super amplitude is uniquely determined by factorization, namely tree-level unitality. And this fact, the absence of supersymmetric contact term implies a linear relation among the coefficient of contact term, contact diagram you will see next slide, and so there's a linear relation between the coefficient of contact diagram and those from the factorization diagram. Okay. Said in another way, the contact term is not independent from factorization because there's no contact term cannot be supersymmetrized. So for this particular amplitude, it gets contributions like for this 6-point amplitude, it got contributions from these 3 types of diagrams. So the first one is a contact term, namely, say you start with d6 r to the 4, you expand or d6 r to the 4 b, you expand another guy, and expand the coefficient of d6 r to the 4 b, one more fluctuation named b bar, and the coefficient of this interaction is d bar e1. Then there's a term like has a factorization property, namely say there's a d6 start to the 4, then you start to attach with supergravity text. This will proportional to the coupling, the coefficient of d6 start to 4, namely I call it E0. There's another type of factorization diagram, namely, so at this order, you can have a factorization diagram take this form, namely 2r to the 4. So this one is not really r to the 4, but it's related to r to the 4 by supersymmetry. So I replace 2 graviton by 2 B fields. Okay. And as I said, the absence of supersymmetric contact term implies this is not independent. Namely, said in another way, this one alone cannot be supersymmetrized. So they must combine with others to be supersymmetrized. Therefore, there's a relation between them. And so there's a linear relation between all of the coefficients. And this is the equation appeared in Michael's slide. So those coefficients, in principle, should be determined if I were able to construct this super amplitude and I were able to compute all of the diagrams. Right? Nevertheless, yeah, that's what I said. Nevertheless, one can just use, say, known data. So in this case, there are 2 numbers to determine. So I just need to, say, use tree level 1 loop to determine these 2 numbers, and turns out this is a number. Then from this first order equation, then you can derive, say, the well-known Laplace equation for E0 or for E1. Okay. So let's look at the more interesting case. Namely, I want to study the coefficient of this 2 6-point interaction. So I call the E2, 1, E2, 2. Again, just like before, to study the coefficient of this 6-point interaction, I like to look at the higher point amplitude. In particular, in this case, I look at the 7-point amplitude. Namely, I expand the coefficient of this interaction with 1 more B bar insert. Okay, by exactly the same argument, namely the supersymmetric amplitude related to this one cannot have any conductance. So the absence of conductance immediately tells me that the coefficient of this conductance should be related to this two factorization diagram, and the same for this conductance. So this leads to two independent first-order differential equation takes this form. Okay. So again, this coefficient are in principle determinable if I'm strong enough to compute the super amplitude as well as those diagrams. However, I'm not able to do that. But so first of all, for the first case, as I mentioned earlier, this E2,1 actually is just related to D6 out of 4 by covariant derivatives. So we actually know what it is. And using that factor, these two numbers can be fixed. Again, what's genuinely new is this guy. So as I said, by construction, this function should not have a tree level term. So I construct the interaction such that it doesn't appear at the tree level. So using this information, actually one can determine one number out of these two. When you do that, you find the first order equation takes this form. And again, from the first order equation, you derive the Laplacian equation for this guy. And so again, this number are in principle determinable if I were able to compute the super amplitude, or since this function started to appear at one loop in string amplitude, so if one were able to compute, say, 6-point string amplitude at one loop to this number derivative, one would also determine this number as well. Okay. Nevertheless, so because this is just up to overall constant, one can solve this equation up to this overall constant. You find this function should go like this in the perturbation at least. So by construction, there's no tree level term. So the tree level will be like a tau 2 to q. So it starts one loop, two loop, three loop, and maybe some then instantaneous. Okay, and this coefficient are say our predictions. From which computation?
I'm sorry, I guess they only know the 4.9.
Yeah, that's right. Sorry? Yeah, I just put that. So there's overall. Yeah, C1 is overall, yes. So it could be zero, I don't know. But probably not, but yeah. So the kinematic factor. I mean how this derivative. So I have this d6. You have to say what d6 means, right? D6 there's contraction, there's Lorentz index, there's like I even don't know like how many contractions can be. So first of all, I'm telling you there's only two possible contractions, and this. Yeah, so polarization already has been taken care of by supersymmetry, so it's inside here. So supersymmetry package all the information about the popularization vector and so on into this data queue. So remember, I have a super field that package all the onshore states inside. So this part take care of everything. And then what's left over is only talk about the derivative and how many derivatives do you have. Okay. Yeah, so once you determine the 6 point, then you can go on. Actually, you can go on to any point, but at this number of derivative. It turns out that they are completely determined by solved. So namely, I will require, say, my n point go to n minus 1 point by this. This requirement turns out that uniquely determine the kinematic structure of n points. It takes this form. And again, the coefficient of those that's supposed to be coefficient. The coefficient of these couplings are related to the lower point by covariant derivative. So in this way, we determine, say, the infinite set of BBS terms. One of them is related to the D6 out of the 4 by solved. And we know the precisely kinematic structure, and we know precisely what are the coefficients. So we know everything about this guy. And there's another set of infinity set of BBS terms. They related to this new guy, so we got 06, 2 by solved. And all those terms are determined up to this one number we call the C1. Okay, let me not repeat it here. So let me just conclude. So in general, so the interaction can be separated into different sets, and those interactions of the same set are related by solved, and the coefficients are related by covariant derivatives. Then for the BBS terms, they satisfy additional constraint from supersymmetry. So here I'm using a method first developed by Xiang, and this additional constraint typically in the form of D-bar equations. From this result, so we actually can make some predictions. In particular, as we said, there's this new interaction which vanished at one loop, so vanished at the tree level, started to appear at the one loop. It would be very interesting to compute this number. So if one were able to do one loop computation. And furthermore, actually, if one look at it carefully about another guy, it turns out, which is supposed to be known, if we look at carefully about another guy, it turns out that this guy only has a tree level, one loop, three loop, but not two loop. So unlike D6 out of the 4, which has one loop, two loop, three loop, and the instant on, but this has absence of two loop. Okay, I think I finish here. Thanks. No. Like which order, first of all?
The thing is, presumably the statement that there are these two allow supersymmetric structure, 061, 062,
yeah,
would also hold in 11 dimensions.
I have to think, is it possible to uplift? I think you had some requirement about whether or not this can be uplifted, right? Yeah, I haven't looked at it, but it's not, I don't know if it's not so trivial whether or not it's upliftable, but